4.3 is on absolute value functions, and you might remember talking about absolute value way back at the start of this course. Do you remember we asked you stuff like, what's the absolute value of -6? And absolute value is shown with those vertical bars there. And if you want to know what the absolute value of -6 is, the answer is 6. Why? Because when you're talking about absolute value, what you're asking is, how far is this number, -6? How far is it from 0 on a number line? And the distance from -6 to 0, the distance from -6 to 0 is 6. Alright, with that in mind, what's the absolute value of +6? A lot of people think it's -6. They think this is an opposite machine, right? But it's not. Again, what's the distance of that number? 6. What's the distance of that number from 0? It's 6. So this is also 6. So the way you probably remember this is, if you have a negative number in the absolute value sign, it becomes positive. If you have a positive number in the absolute value sign, it stays positive. Okay? Now what we're going to learn about is how to graph absolute value functions. We're going to learn how to solve absolute value equations. So it's all about absolute value functions. And basically what an absolute value function is, it has the form y equals the absolute value of fx, where f of x is a function. So the first thing we're going to learn to do here is we're going to learn how to graph absolute value functions. We're going to graph y equals the absolute value of x. And this is the most basic form, so yes, you could call this the mother function. So we don't know how to graph this right now. We don't know what it looks like. So whenever you don't know how to graph something, the way you can almost always graph it is you make a table of values. So let's do that. And we're going to graph some x values. We're going to put some y values. And since we're talking about absolute values, you better make sure you use some negative values. Better make sure you use some positive values. Why don't we use the values -2, -1, 0, 1, and 2. That should be good. If you put -2 into x, you have the absolute value of -2, which is 2. The absolute value of -1 is 1. The absolute value of 0 is 0. The absolute value of 1 is still 1. And the absolute value of 2 is 2. So if we graph this, we have a point at -2, 2, a point at -1, 1, a point at 0, 0, a point at 1, 1, and a point at 2, 2. And I think you can probably guess that what happens is this keeps going up here forever. So you should put arrows on it like that has. And it keeps going up here like this forever. And that's what it looks like. So now let's do another method of solving this. Or another way we can solve this is by graphing y equals x. Let's graph that and see how we can use that graph to get this graph, because we don't want to use a table of values every time. Sometimes that can be a little complicated. Okay, believe it or not, y equals x is in slope-intercept form. Remember y equals mx plus b, where m is the slope and b is the y-intercept. Hopefully you remember this. Anyway, if you look at y equals x, what's the number right in front of right in front of x? In other words, what's the slope? Well, in this case, the slope is 1. Okay? And what's the y-intercept? Well, there is no number out here, so it's kind of like y equals x plus 0. The y-intercept is 0. So we can graph that. This is like the mother function. Y equals x is actually like the mother function of lines. It has a y-intercept of 0, so that is right here, and it has a slope of 1. So up 1 over 1, up 1 over 1, up 1 over 1. You can see it's exactly this line like we'd expect, but it doesn't go up here. It would be down 1 over 1 this direction, down 1 over 1 this direction. So the line y equals x actually looks something like this. Okay, how would that help us to draw this line? Well, as you can see, all the points on y equals x stay exactly the same, as long as they're in this part of the graph. But once the points are down here, they don't stay down there, they kind of bounce up to here. Why would that be? Well, look, this is an absolute value sign. Is it possible, if you look at the table here, for example, is it possible to have a y value that's negative? No, because any x value that's negative or an x value that's positive is always going to be positive because of the absolute value signs. So it's impossible to have any points down here because all of these points have negative y values. So what happens is all these negative y value points, like this point for example that was at -1, goes up to +1. This point here was at negative 3, it goes up to positive 3. This point here, for example, is at negative 7, it goes up to positive 7. So basically, the steps to solve an absolute value graph are the following. First of all, graph the function inside the absolute value bars. So instead of graphing y equals the absolute value of x, I just graphed y equals x. That's what this green dotted line is. Then the second step, move all the points that are below the x-axis, all the points down here, just move them up above the x-axis, making them the same distance, right? This point right here was 3 down from the x-axis. Now I move it so it's 3 up from the x-axis. And you just do that everywhere, and you'll have the answer. Alright, let's try another one. Y equals x squared plus 2x minus 3. So, first thing we're going to do is we're going to graph y equals x squared plus 2x minus 3 with no absolute value signs on it. Okay, what's this going to look like? You should know, look at this x squared. What's that going to make? It's going to make a parabola. So this is not in standard form, unfortunately. So we could either complete the square on this, but what might be quicker in order to graph this is to use negative b over 2a. This will help us find the x value of the vertex. So negative b would be negative 2 over 2 times a, and the a value is 1. So we get negative 2 over 2, which is just negative 1. So the vertex is at negative 1, comma, what's the y value? Remember how to get the y value? Take this negative 1 and plug it into that x and plug it into that x. So why don't I do that right here? Y equals negative 1 squared plus 2 times negative 1, take away 3. Negative 1 squared is 1. 2 times negative 1 is negative 2, take away another 3. 1 take away 2 is negative 1, take away another 3 is negative 4. Okay, the vertex is at negative 1, negative 4. So, negative 1, negative 4, right there. Great. What's the a value here? The a value is, if I look here, the a value is 1. So it's positive. That means it's going to be a parabola facing up. And it has a value of 1 is beautiful because it's congruent to the mother function. We could just use the step pattern for this. Remember the step pattern? We go over 1 and up 1. And then over 1 and up 3. And then over 1 and up 5. And then over 1 and up 7, so it would be somewhere way up here. And then by symmetry, we can do the other side. So it would look something like this. This would be way up here somewhere. And we can join all this together. But maybe I don't want to join it all together. Do you know why? Because remember, what I actually want to graph is the absolute value of this. We can't have any points that are below the x-axis, can we? So these points down here are actually going to end up here. Do you want me to graph it first and then I'll show you what I'm talking about? Maybe I'll do that. Okay, I did the best I could. I know it's not great. Okay, so what I've graphed here is y equals x squared plus 2x minus 3. But I want to actually graph, now that I've got this, I can quickly use this to graph y equals the absolute value of that. All the points here, all these points, this graph, it's all great. This is all positive y values. Those are all good. All the points here are good. These are all positive y values, so those are all point. We get to two very important points. These points right here on the x-axis. In fact, we have a name for them that I'll just put down here for you. The x-intercepts are called critical points, and the reason they're called critical points is because this is where the graph changes directions at these points. So right now, if you look at this graph, it doesn't look like the graph changes directions there, but it will, and the reason it's going to change directions is because of the absolute value signs. The absolute value signs means that there can be no points down here below the x-axis. So this point down here, which is at negative 3, is going to move up to positive 3. This point, the vertex, which is at negative 4, is going to move up to positive 4. This point here, which is at negative 3, is moving up to positive 3. So, in fact, the parabola is not coming down like this. It's going up like that. So, I guess what I should do now is to get rid of this. This is why I said maybe you don't want to actually draw this in the first place. Like that. And there you go. We have now successfully graphed this right here. One thing I wanted to mention is you'll see that I have said that we're going to graph things where it's y equals the absolute value of f of x. And that's what we're doing. But you could also graph things like this. Y equals, I don't know, x plus 2, and then minus 3. you could have a bit outside, or you could have like y equals 2, and then the absolute value of x squared or something like that. Again, you have something outside of the absolute value sign. We're not going to do that this year. We'll do that next year, because we do more absolute value functions next year in grade 12, and I figure, hey, let's not do too much this year. Let's save some of that good stuff for next year. It's actually quite a bit more difficult. So we'll save that for next year, and for this year, all our functions, the entire function will be inside the absolute value sign. Okay, so that's basically all I wanted to say about graphing absolute value functions. Let's move on. Okay, the other thing I need to teach you about in this lesson is piecewise notation. This always gives people fits, but you will get this. It's not as hard as it's going to seem at first. Basically, what piecewise notation is, it's just saying that if there's an absolute value function, you could write it in another form, and this other form would have two pieces to it. That's why it's called piecewise notation. So here you go, blow your mind here. Y equals the absolute value of f of x is the same as y equals f of x if f of x is greater than or equals 0, and negative f of x if f of x is less than 0. Okay, that's scary, right? Maybe an example will help here. We graphed on the other side of the page y equals the absolute value of x. And what we're saying here with piecewise notation is writing that y equals the absolute value of x is the same as, like another way of writing that, another way of writing y equals the absolute value of x, you could just say that y equals x, because sometimes they're exactly the same. If you take a look, I've cleaned this all up here, and I've left us with the dotted line, which is y equals x, and the v, which is, I don't know why this is gone, which is y equals the absolute value of x. And you can see for some points they're exactly the same. Namely, all these points, they're exactly the same. This part of the graph is the same whether it's y equals x or y equals the absolute value of x. So you could say that y equals the absolute value of x is exactly the same as y equals x, but not always. When's that true? For which x values is it true? It's true for all these x values, and all those x values are positive. They're all greater than or equal to 0. As long as a point is 0 or 1 or 2 or 3 or 1.5, as long as it's a positive x value, y equals the absolute value of x is exactly the same as y equals x. So that's why the first part we're going to say is that y equals the absolute value of x is exactly the same as y equals x if, that's my if the x value is greater than or equal to 0. But that's only half the battle, right? There's some of them, namely when x is less than 0. If x is less than 0, it's not true that it's the same. What happens with all those points where x is less than 0? That's all these points down here. These are all x values that are less than 0. Negative 1, negative 6, all have x values less than 0. And they don't end up on the same graph. What happened is this point here, for example, which is at negative 2, negative 2, and it moved up to here. So it's now at negative 2, positive 2. So what happened is the point that was negative 2 became positive 2. Now, how do you make a value of negative 2 equal to positive 2? Well, I know what you're saying. You're saying put absolute value signs on it. That's great. That's true. But can you think of another way you could make negative 2 become positive 2? You could put a negative sign on it. Make it negative negative, because two negatives make a positive. So that's what they're saying here when they say that it's equal to negative x if x is less than 0. Right? Again, because for all these points down here, we're changing them from a negative y value to a positive y value, and the way you can change a negative to a positive is by making it a negative negative. Oof, I know, it's awful, isn't it? Okay, but it's really not that bad. So here we go. We're going to write these two things in piecewise notation. So the first thing we want to do is we want to figure out when is it that these absolute value signs here do nothing, like they actually have no impact. Well, when they'll have no impact is when the part inside, the negative 4x plus 4, is either greater than 0 or equal to 0. Because remember, if this amount in here is positive, the absolute value signs do nothing to a positive number. If that amount inside there is 0, absolute value signs don't do anything to 0, it still stays 0. So this is what we have to solve. We have to find when is that amount inside the absolute value signs, when is it greater than or equal to 0. Okay, well let's solve that. I'll subtract 4 from both sides, so I get negative 4x is greater than or equal to negative 4, and then I'm going to divide by negative 4 and divide by negative 4. Careful! When you have inequalities and you divide by a negative, what happens? It flips over. So negative 4 divided by negative 4 is 1. X is less than or equal to 1. So what they're saying now, what we figured out is that y equals the absolute value of negative 4x plus 4 will be exactly the same as, well, the absolute value signs do nothing. In other words, it'll be equal to negative 4x plus 4 if x is less than or equal to 1. But what if x is greater than 1? Well, then what it would be equal to is negative all that stuff inside there. Negative 4x plus 4. And negative 4x plus 4 equals positive 4x and negative 4. This negative refers to both things. It's like the negative 1 if you want times those. So minus 4. This is your answer. Okay, let's do one more. This one's a little more difficult because it has a quadratic in here. So the first thing we're interested in, when do the absolute value signs do nothing? The absolute value signs do nothing when the part inside the absolute value sign, negative x squared minus 4x minus 3, as long as that amount is greater than 0 or equal to 0, then those will do nothing. So we got to solve this now. Alright, well, unfortunately, to solve a quadratic inequality, don't know if you remember this, you are temporarily going to think of it as negative x squared minus 4x minus 3 equals to 0, and we're going to solve it. Now, how do we solve that? Well, I don't like this negative here. Let's move everything to the other side to get it positive. So move that over, it becomes x squared. Move that over, it becomes plus 4x. Move that over, it becomes plus 3. And the way we solve quadratics is we factor, and so this is a simple trinomial, x and x. Two numbers that multiply to 3 and add to 4, 3 and 1. Bring down the plus, positive times a positive. Now we use the zero product property. Either x plus 3 equals 0 or x plus 1 equals 0. Solve this, subtract 3 from both sides, you get x equals negative 3. Subtract 1 from both sides, you get x equals negative 1. And we're not done yet. You know what you do now? You put it on a number line. We've got negative 3, we've got negative 1. We've got to figure out what kind of dots to put. Well, if we look back up at the start, it's a greater than or equal to, which means we're going to put solid dots. Now we need to try either all three of these sections if you want to be really careful, or just try one of them if you want and alternate. I'll try up here because 0 is always an easy one to try. So I don't try it in the temporarily one, I try it back up here. I'm going to put 0 in there. So I get 0 squared, well it's still 0. Take away 0, 4 times 0 is 0. Take away 3. So I end up with negative 3 is greater than 0, or greater than or equal to 0. Is it true that negative 3 is greater than or equal to 0? No, that's not true. So this section here did not work. If this one didn't work, this one will work, and this one won't work, right? They alternate. So this is the only one that works in here. So what it looks like is that. Know how to write that? We say negative 3 is less than or equal to x, which is less than or equal to negative 1. This is where the absolute value signs have no impact. So now we can write our answer. What we're saying is that this, y equals the absolute value sign of all that, is exactly the same as negative x squared minus 4x minus 3. The absolute value signs do have no impact as long as negative 3 is less than or equal to x is less than or equal to negative 1. As long as our x value is between negative 3 and negative 1 inclusively, then it has absolutely no effect. But what if it's not between those? What if it's either down here, so that would be x is less than negative 3, or if it's up there. It can't be and, it can't be both. So, or if x is greater than negative 1. What happens then? Then it's not exactly what's inside the absolute value sign. It's going to be negative of that amount. So what's negative of negative x squared minus 4x minus 3? Well, this negative refers to everything. So the negative x squared becomes x squared. The negative 4x becomes plus 4x, and the negative 3 becomes plus 3. And this is our answer. Let me quickly show you one last thing about this down here. If you looked at this part of the graph, there and there, that was just the same as the original parabola, the y equals x squared plus 2x minus 3, right? No different. But if you look at this part of the graph, it's different. Now, how is it different? Well, what we've just been saying is how it's different is you just take negative of all this. So it's y equals negative x squared, negative 2x plus 3. So what I'm saying is that this graph right here must be that right there. Want me to prove it to you quickly? Why not? Let me show you. If I was to find the vertex of this, it would be negative b over 2a. Negative b would be negative negative 2 over 2 times negative 1. So that's 2 over negative 2, which is negative 1. And then if I want to get the y value, I put negative 1 into all these. So negative 1 squared, take away 2 times negative 1 plus 3. What's that equal? Be careful here. Negative 1 squared is positive 1, but then there's a negative. So negative 1, negative 2 times negative 1 is plus 2 plus 3. So negative 1 plus 2 is positive 1 plus 3 equals 4. The vertex should be at negative 1, 4. Negative 1, 1, 2, 3, 4. Yes, that point right there is negative 1, 4. It's perfect. This has an a value of negative 1. Negative means it faces down. Yes, this does face down. And it's negative 1, which means we can use a step pattern. Over 1, down 1. Over 1, down 3. 1, 2, 3. You see that? It works. So it's a tricky concept. You might have to look at a few examples, maybe rewatch some of the video, but hopefully you'll get piecewise notation. Good luck.